All right, let's take a look at section 7.1. Okay, chapter 7 is all about transformations. Okay, the kind of transformations we're going to look at first are what we call rigid motion. Rigid motion, as I just explained, doesn't distort something. It just takes what you have and either rotates it, reflects it, or translates it to a new spot. But it stays exactly the same size as it was originally. Yeah. Yeah. Okay, when we do a transformation, okay, we have what's called an image and a pre-image. Okay, the pre-image is what you start out with. Okay, think of pre means before you do anything to it. The image is what you get after. Okay, and we'll try to come up with like a way that you know, if you're looking at a picture, which one is the original and then which one is the transformation. Our book generally uses red and blue, okay, for one or the other. Okay. Yeah?
So in this section, we're going to be enlarging objects.
Well, think about that, enlargement. Would an enlargement fall under reflecting, rotating, or translating something? What do you think? Would an enlargement be rigid? Meaning it stays exactly the same size after the transformation. Well, Connor, what do you think?
I think it's translated.
So, so his question was, is an enlargement something we're going to study in this section? What do you think?
I think we would.
Think we would? All right. So that means when you do an enlargement, it's staying exactly the same size. Because we're only studying transformations in this section that keep things the same size. Would an enlargement do that? No. An enlargement's going to make something bigger. Okay? So enlarging things and reducing things, we're not going to study that in this section. Okay? So the operation that creates your image, that's called a transformation. Okay, and when you do a transformation, you can really get into a lot of computer programming here, like an animation. So you might have an object on the screen, and you want to take that object and you want it to move somewhere else on the screen, like if you're animating something, or maybe, let's say, in a movie, one of the characters is looking into a mirror. You want to create a mirror image of that person in the mirror, because that's what it is. Mirrors reflect everything. Well, there's a lot of mathematics in how you can do that, and that's all computer animation. Okay. We won't really be studying that here, but that's kind of one area you could go with all these transformations, computer animation and things like that. Okay, so we're going to look at 3 different transformations below. And the figure in blue is always going to be the pre-image. And the one in red is going to be the image. And that's how your book does it. Blue is the figure you start with. Red is the transformation. Let's start out with a reflection. Okay, so a reflection, generally we have a line. It doesn't have to be vertical or horizontal. I could have it on an angle. But the point is, wherever my line is, I reflect over that line. So if you compared the image and the pre-image, okay, the pre-image is in blue. The red one is the image. Are they the same size?
Yes.
Yeah, they're the same size. In fact, if you picked any point on the pre-image, say the tip of the lower part of that F, and you measured to the line of reflection, and then you picked the tip of the lower part of the red F and measured that distance, what do you think those two distances, if you compared
It
them?
should be the same.
Yeah, they'd be the same.
Well, it should be, doesn't
Yeah.
mean they are.
Yeah, they should be. They always should be.
Question everything.
So that's one technique to draw a reflection. All you have to do is measure distances to the line you're reflecting to and make sure they come out the same on each side. And then you've created a reflection. Okay, so that's a reflection. Okay, that's a rotation. In this case, I'm rotating. We don't rotate over a line, generally. Okay, when you rotate, you pick a point, and then everything rotates around it. All right, so in this case, my point is in black. The blue F, that's the original. Okay, that's the pre-image. And the one in red, that's the image. Okay, and we did a rotation. How much did you rotate? Well, I kind of tried to draw in something to show you. Okay, there's your point of rotation. If you take and put a line from that point, and then pick a spot on the F. So in this case, kind of this little corner right there. And then do the same thing here. Draw a line from where you rotated to the same point, right in that little corner. Now, if you had a protractor and you measured this angle, that's the amount of rotation. Do you think you have to pick those 2 points exactly? No, I could pick any 2 points as long as they're corresponding. I could pick the upper left part of the F there and the upper left part of the F there. If I drew in 2 lines, the angle would come out exactly the same. Right, so that's rotation. And last one is translation. Okay, so translation, all you're doing is taking an object, think of it as sliding it. Okay, you're sliding it in a direction. Your book will generally put an arrow, so that kind of helps you figure out where you're sliding to. So blue is pre-image, the red is in image. Bless you. Okay, and the way that I drew all those is exactly how your book will do it. Pre-image is in blue, image is in red. Now sometimes we have multiple transformations. Like, we're not going to get into it here, but you do a rotation and then you reflect it. So you do 2 things. I think when we start to get into multiple ones, they use blue, red, and green. Okay, but the color doesn't matter. So if you look at a different geometry book, they probably use different colors. Okay, well, if we're doing this on paper, kind of the problem with the colors is unless you have different colored pencils to draw it, it can be kind of confusing. Okay, especially on the test. All right, so what we'll do is we're going to come up with a different way to show on paper, just using one color with labels. Okay. So what we'll do is we're going to take a pre-image and we're going to label it just like we normally would. Okay. So there's a pre-image. And I labeled all the vertices, A, B, C, D. When I translate it, I'm going to do it in red so you can see the color difference. But I'm going to change all the labels. I'm going to add prime symbols to all the corresponding vertices on the image. Anybody know what a prime symbol is? What that looks like? Yeah.
Subscript.
No, not a subscript. This one's actually up higher. It's more like a superscript. But it's the right idea. It's a little bit different spot. Just basically a little vertical line. Almost looks like an exponent of 1. Okay, it's not, but it's just a little vertical line. Okay, and what you do is you compare A to A prime. Okay, so this point in the pre-image went to this point in the image. Okay, how do I know that? One's labeled A, one's labeled A prime. Tells me these are corresponding points. Okay? point B in the pre-image, and that's where it went to in the image, B prime. Okay. Point C went to C prime, point D went to D prime. Now it's very easy to tell which one is which, even if you're not using color. All the ones with primes are the image, without primes, pre-image. What kind of transformation is this? Or what do you think it looks like?
A slide to the right.
So what's the name of that one? That's a
Translation.
translation. Yep. This one is a translation. Okay, and the way you pronounce it, I already said that. B prime, C prime, D prime, A prime. Okay, any questions on that? Now, what if you did another transformation to this one in red? So let's say we took this and then we made it's going to be hard for me to do by eye, but then did like a mirror image of it. Okay, something like that. How do you think you would label this point now? It's very similar to what we did the first time.
Upside down vertical line.
Something, yeah, you're going to use a prime again, but you can't call it A prime, because A prime with just a single mark is when you did it once.
It has to be 2 mark.
Yeah, so what we could do is call it A double prime. So this is where A goes in the second transformation. Okay? And then this is where D goes. Okay? This is where C went. And this is where B went. Okay, we're not going to get into multiple transformations, but I'm just kind of showing you how that idea can be extended to as many transformations as you want. All right, so there's a picture of a transformation. And they want us to describe what it is. So your choices are translation, rotation, or reflection. And then if we know which one it is, we'll try to describe, how many units did it move, things like that. Okay, what kind of transformation is that? Yeah.
Reflection.
That's a reflection, yes. Okay, it's a reflection. Can anybody be a little bit more specific? So when we reflect, we normally reflect over a line. Can anybody describe to me, what did you reflect over here? Yeah.
Y-axis.
Yeah, you reflected over the y-axis. Good, very good. Okay, so that's how you describe it. Reflection over y-axis. Okay, even if there was no color, which one is the pre-image here? How do you know?
The prime.
The pre-image?
Oh.
So the one before you do anything, Luke?
The one without the
Yeah.
one with the blue.
Yeah, the blue, the one without the primes. That's the one you started with. The primes is the one you ended up with. So basically, we flipped this figure to the right. We flipped it to the right. Yep.
So even if we do have colors, you still want to strike the primes?
Yeah, we'll stick with the primes. Most of the time, people don't have like separate colored pens with them, so that's fine.
Even if it's on the color.
Yeah. So yeah, we'll stick with the primes most of the time. I'll try to do both on the board just to help you guys out a little bit. Okay, next part, I want to name the coordinates of the vertices of the image. Okay. How many vertices are in the image? Yeah?
6. 3.
3, yeah. 3 vertices in the image. Okay. What are the 3 vertices in the image? About area? You don't have to give me the coordinate, just tell me their names. Yes, in the image, the 3 vertices are A prime, B prime, and C prime. They didn't ask for the pre-image unless they're going to ask for that next. No. All right? So A prime, B prime, C prime. And they just want to know the coordinates. Okay, so A prime is, let's see, 4, 1. 4, 1. C prime, that one's easy, that's 1, 1. And B prime, let's see, 1, 2, 3, looks like 3, 5. Okay, so that kind of question is just testing to see, do you know which one is the pre-image, which one is the image? Okay, and the last question, is the original triangle ABC, pre-image, is that congruent to its image? Are those two triangles congruent? What do you think here?
Yeah.
Yeah. They're congruent, basically you could say by side, side, side. Okay? All the sides stayed the same length when you reflect it. No lengths changed. So those two triangles are mirror images, but they are congruent. So, yes. All right, so I've talked a lot about this idea that transformations, the one we're studying today, they don't change the length of anything. Well, if a transformation doesn't change the length, that's called an isometry. Okay, isometry. So transformations that do not affect lengths are isometries. So we just saw with a reflection, when you mirror image something, lengths don't change. So a reflection is an isometry. How about a rotation? If you rotate something, do the lengths change? No. So a rotation is an isometry, and so is a translation. You just take something and slide it, doesn't change the lengths. Those are all isometries. Okay, here's some other things that also happens. Area stays the same. If you take a rectangle and rotate it, it doesn't change its area. If you take a rectangle and translate it or reflect it, its area stays the same. Angle measures stay the same. Okay? If I took a triangle and translated it, would that change any of the angles just by sliding it? Think here? No. Okay? So angles don't change if your transformation is an isometry. Parallel lines are also preserved. Take a parallelogram and rotate it. Okay? No matter how you rotate it, the original sides that were parallel are still parallel. Okay, so let's take that shape, rotate it. Okay, no matter how you rotate it, parallel lines always stay parallel. Okay, if I take and slide it, well, parallel lines are still parallel. And then if I did a mirror image of it, I can do that by just, they call it flip, we call it reflect. I just reflected it. Lines are still parallel. Okay, so parallel lines are preserved. So another name for a transformation that's rigid, okay, we can call it an isometry. We can also call it a rigid motion transformation. There's no distortion. There's no change in the size of or the shape of the figure. Now, there is another transformation that will preserve angles, but it won't preserve the lengths of sides. Can anybody think what transformation that would be? It's not one we're studying today. All the angles would stay the same, but the sides would change. Yeah? Yes, an enlargement. Very good. So an enlargement or a reduction. All the angles stay the same. Think of an equilateral triangle, then think of a larger equilateral triangle. The angles are all the same. They're all 60, but the sides change. Okay? That's not a rigid motion transformation. Okay? An enlargement or a reduction is not an isometry. So I want to look at some pictures, and just the best that you can tell, I want you to tell me which ones look like they're isometries. Okay, example 2A. Does that look like an isometry? You think, Tanner? Yeah, that is an isometry. Anybody you have a guess what transformation it looks like? That is a reflection. That's a reflection. So yes, that is an isometry. How about example 2b? Is that an isometry? What do you think? Luke? No. No. What does that look like? We haven't studied it, but it kind of looks like it's like a reduction. Everything's been reduced proportionally. Okay, so this is not an isometry. Okay, how about this one? What do you think? Does that look like an isometry?
Well, yes, but no.
Well, it can't be both.
It looks longer.
It looks longer? Sure.
I don't know. It is on.
So yeah, that is an isometry. It's just a rotation. Generally, when you see a dot and then you see a line drawn to corresponding vertices, that's telling you it's a rotation. All right, so yes, this is an isometry. Okay, I'm not going to give you one that's kind of tricky where it's like, well, it looks like it could be, but it might be like a ½ inch off. No, it's either going to be very clearly an isometry or not an isometry. Okay. All right, so when you have to kind of describe this transformation, sometimes we call it a mapping. Okay, a mapping is how you do the transformation. So in this picture, this is a translation. And we can say that triangle ABC is mapped onto triangle A prime, B prime, C prime. The order is very important. When you write ABC, and A is first, B is second, C is third, and then you write A prime, B prime, C prime, you're saying that A goes to A prime. You're saying B gets mapped to B prime, and C gets mapped to C prime. It's kind of like when we write congruent triangles. You've got to have the order correct. You could not say this. Triangle, let's see, ABC is mapped onto triangle BAC. That's wrong. A doesn't go to, or actually those have primes. A doesn't go to B prime. A goes to A prime. So you could say it in different orders. Anybody give me another order here that would be okay besides ABC, A prime, B prime, C prime? Be a different order you could say that in. Yeah?
CBA and C prime, B prime, A prime?
Yeah. C, B, A, C prime, B prime, A prime. Yeah. You just have to be just consistent like when you do congruent triangles. Okay, so that's a mapping. Triangle ABC is mapped onto A prime, B prime, C prime. Just another way to describe it. Okay, if you don't want to write out the words is mapped onto, you can just use an arrow. Now the arrow doesn't mean translation. You could use that with a rotation too. All you're saying is that whatever transformation you did to get from the one on the left to the one on the right, A is going where A prime is, B is going where B prime is, and C is going to C prime. Okay, we already said this. Order in which you write the vertices, that specifies which vertices correspond with each other. So A to A prime, B to B prime, C to C prime. If you wanted to do the triangle BAC, B prime, A prime, C prime, that's fine. Just keep that correspondence in the right order. Anybody know how many different ways you could do that? Basically, if you look at the letters A, B, and C, how many different ways you can arrange them? There's six. 6 different ways to write ABC. Okay, you don't have to know that, but that's just how many ways there are. All right, so in the diagram below, it says that PQR is mapped onto triangle XYZ. Notice they didn't use primes this time. Instead of doing like P prime, Q prime, R prime, they just decided to use different letters. That's fine too. But what they're telling me is P goes to X, Q goes to Y, R goes to Z. Okay, and the mapping that we're looking at is a rotation. Okay, since it's a rotation, that means it's an isometry. They want me to find the length of XY. And then they also want me to find the measure of angle Z. Okay, how could you find XY based on what's in that picture? Nothing's labeled on the image, but there is some stuff labeled on the pre-image that'll help us. Yep, Selena? Yes. Yeah, so since PQ and XY are congruent, they're the same length. Okay, so if PQ is 3, then XY is 3. Okay, so XY equals 3. How about the measure of angle Z? Who can describe that kind of the same way? Luke?
Angle Z is congruent to angle R, so it's 35 degrees.
Yeah, angle R and Z are both the third letter. They're congruent. Since they're congruent and we know R is 35, that means Z is 35. Okay, just using the very simple idea that side lengths and angle measures do not change in an isometry. Okay, the next one says you are assembling some pieces of wood to make a railing. And the first question asks me is how pieces 1 and 2 are related. Okay, how could you describe that? How are pieces 1 and 2 related in that railing? Like, let's say, these pieces, they come in half pieces. So each section of this railing is really 2 pieces put together. So think of it that way. Yeah.
They're reflections of each other.
Yeah, they're reflections. So if you had a machine that was cutting these out of wood and it could only cut half a piece at a time, that's all you would really need to cut. You could just cut one piece, and then when you put it in, reflect it, just flip it around the other way when you put it in the railing, and then you can get that design. Okay, it's a mirror image. Okay, so pieces 1 and 2 are reflections. Okay, how about pieces 3 and 4? How would you describe that? If you had piece 3 and then put it in piece 4's spot, what kind of transformation would that be? Yeah, that's a translation. Okay, so just trying to get you to see these transformations in kind of like a real world object. Okay, and the last one. Here we're looking at a blueprint that's basically the top view of a kayak. Okay, but it's just half of the kayak. Okay, it's just like the top half of the blueprint. It says, what type of transformation could a builder or an engineer use to visualize the entire kayak based on that blueprint? What kind of transformation would the builder be able to use? Alyssa? Yeah, it's like a reflection. Okay, on the smartboard, they call it a flip. But if I take this, make a copy of it, And then if I flip it, would I flip it vertically or would I flip it horizontally? Yeah, vertically. Flip it, so that's up, down. Okay, so now if we kind of put it together, we can kind of visualize the entire kayak. Okay. All right, now it says, what would be the maximum width of the kayak? So the width changes. Some parts the width is very narrow, it gets wider in the middle. But what would the maximum width be? And how do you know that? Denver? Yeah, how do you know that? Yeah, the top part has a maximum width of 10. So if you reflect it, you just doubled the maximum width of the top part. So you got 10 on the top, 10 on the bottom. At its widest point, it's 20 inches. Okay, so there's a kind of a quick introduction to transformations. What we're going to do basically for the next 3 days is we're going to spend 1 day on each transformation. Okay, we'll do reflections tomorrow, and then we'll do rotations the next day, and then we'll stop because we have our test, and then the next week we'll pick up with the rest. Okay. So the homework is on $3.99. 12 to 21 all, 23 to 31 odd, 35, 41, and 44. Okay, for MCAS, finish the multiple choice. So 9 through 12 on the MCAS.